We'll get started with chapter 1 from Young and Friedman. Chapter 21 is all about electric charge and field and forces. For those of you who like the biological applications, here's something neat. Sharks actually have the ability to locate prey that are completely hidden beneath the sand at the bottom of the ocean. What happens is that they can sense the weak electric field produced by the muscle contractions in their prey, the things that they're hunting. The sharks, they actually have electric field sensors. Okay, that's kind of neat. Just like nose is a scent sensor and eyeballs are a light sensor, sharks have electric field sensors. And those sensors are little canals, um, and they're filled with jelly, and it leads down to pores in the skin. So the sharks can detect electric fields as weak as about a half a billionth of a newton per coulomb. That causes the charge to flow within the canals inside the shark, and it triggers a signal in the shark's nervous system. These canals have different orientations, so the sharks can measure or sense different components of the electric field vectors and determine the direction of the electric field. That lets them find the prey just by sniffing out the electric field around them. I think that's pretty nifty. Okay, so for chapter 21, most of this was covered pretty well in Physics 1051. In this chapter, all we're really going to focus on is the electric field due to continuous charge distributions. And we'll also do a review of electric charge and fields by talking about electric dipole. It's pretty interesting and it does make for a good review. You're probably pretty familiar with chapter 21, most of these sections right here. The background of what I assume you know is about the nature of charge, the fact that we have two kinds of charge, positive and negative, where protons are positive, electrons are negative. We know neutrons are neutral. The fundamental unit of charge E is 1.6 times 10 to the minus 19 coulombs, and all charge is quantized. Every charge, except for quarks because they're weird, is a multiple of that fundamental charge E. We know that protons don't move more or less, electrons can be free to move. Charges move freely through conductors, not so much through insulators, and they may or may not move through semiconductors. For electric force, we know that that's given by Coulomb's law, and we know that like charges repel and unlike charges attract. We can find that force using Coulomb's law. In Coulomb's law, we have Coulomb's constant K times charge 1 times charge 2 divided by the distance between them squared. So if we had two balloons with the same kind of charge, balloon 2 would be repelled by balloon 1. So there's the force on 2 because of 1. The unit vector notation, R12 here, R12 is the distance between balloons 1 and 2. This unit vector is a vector of length 1 that points from 1 to 2. So that's how we find our force with this unit vector notation. When you use this notation, it's very important that you keep the signs of the charge. If you prefer not to use this unit vector notation, you can use Coulomb's law to find the magnitude, using the magnitudes of charge, and then you'd find the direction knowing that like charges repel and unlike charges attract. So you're probably pretty familiar with the forces. If you asked what's the agent of the force, the answer would be the electric field. An electric field is what tells an electric charge what force to feel. So we might have a source charge Q, and we might want to find the electric field at point P. We know that electric field is the force per unit charge, so it would be K times Q over R squared. R would be the distance between Q and your point, K is your Coulomb's constant, and capital Q is your source charge. So this charge Q makes an electric field that we could measure at point P. Again, the unit vector notation, the unit vector is a vector of length 1 from our charge towards our point, and in this expression we would use the sign of the charge. If you didn't like to use the sign of the charge, then you would find the magnitude doing K times the magnitude of Q divided by R squared, and you'd remember that electric field points away from a positive towards a negative. You should be able to calculate the electric forces and electric fields due to groups of point charges, and you would have to do that using a vector addition. I'm going to assume you're very comfortable with vector use, so for components and unit vector notation. And then last, I'm going to assume that you're pretty comfortable with drawing electric field lines. We're going to go through a review of these concepts with an example we didn't talk much about in Physics 1051, and that's the electric dipole. An electric dipole is what you get when you have two charges separated by a small distance. An important example of an electric dipole is a water molecule. It has two hydrogens, which are positive, and an oxygen, which is negative. They bond as a triangle, and while the total molecule is overall neutral, it turns out that the oxygen end is slightly negative and the hydrogen end is slightly positive. One of the impacts is that water molecules overall are pretty attracted to each other. That results in a high boiling point, which means that water remains liquid at our normal living temperatures. Another thing about the dipole nature is that it makes water an excellent solvent. So, for example, if we have regular salt, NaCl, and we put it in water, the sodium ion, which is positive, would be attracted to the oxygen end of the water molecule, and the chlorine ion, which is negative, would be attracted to the hydrogen end of the water molecule because that's positive. That means that the sodium chloride dissolves. It comes apart and it dissolves into water. This process happens for many, many compounds placed in water. That's important to our life overall because so many biochemical reactions only take place in aqueous solutions like blood. Okay, now let's work on finding the electric field around an electric dipole.